One of the great inventors of calculus is Newton, and he developed a really cool procedure to find the zeros of a function. This is very similar to the bisection method that we've already seen. So here's the idea. First of all, we need to start with a function. So let's create a graph that looks like this function, and we'll call it f of x. And I've given some x values on the axes there, where I can see there's a couple roots. One of the roots is somewhere between 0 and 1, and another root's between 2 and 3. We're going to go get the basic idea of how Newton's method works through finding that root between 2 and 3. So the first step is to start with some initial guess of an x value that we think is kind of close to our root. In this case, I'm going to guess my initial one at x0, I'm going to make equal to 3. So when I do that, the next step is to calculate the point on the graph, f of 3. And take a look at how the tangent line behaves at f of 3. So I think the tangent line looks something like this red line in here. And you'll notice that that then hits the x-axis approximately here. And we do that again, and we end up with a new value. And then we take the tangent line, I'll do that one in blue. It looks like this. And we hit another value here, and we do it again, and again, and again. And we quite quickly, much faster than the bisection method, we very quickly get a good estimate of where that root is. So here's the steps again. Start with an initial guess, x0 close to our root. Then we use the tangent line equation to calculate a new x value, x1, which would be this value here. Then we repeat. We then use that tangent line equation for this point of x1 evaluated, f of x1. We use the tangent line equation there to find x2, and we continue to do this until we get an approximation for our root. This idea of continuing the pattern and coming back and then finding the tangent line and coming back to a new x-intercept and coming back is called an algorithmic approach. And each time we do it, it's called an iteration. So we start off with x0, and then we go to x1. The process is an iteration. Then we go to x2. That's called an iteration. Here's a formula that helps us do those iterations. By the way, this is how the graphing calculator actually works. It doesn't use the bisection method. It uses Newton's method to find zeros, and it can do these iterations using this formula very quickly. Here's the formula. So we start by choosing our initial guess, and then we find subsequent x values until we're happy. By using this particular formula, it's x sub n plus 1. So that's all subscript. So to find the third one, that's 2 plus 1. Find the third one is equal to, you need the previous value minus the function evaluated at the previous value divided by the derivative of that previous value. Okay, so this is each successive value of x. And this part over here is found by rearranging the tangent line equation with y equaling 0. And the reason that y equals 0 is because we're dealing with x-intercepts. So let's take a look at this in action. We're going to approximate a root of this equation, f of x is equal to x squared minus 11, using 3 approximations of Newton's method. We'll see how close we actually get just by doing this iteration 3 times. And we'll start with an initial guess of x is equal to 3. And x is equal to 3 is kind of close because 3 squared minus 11 is pretty close to 0. But we want to find the root, which is like the 0 of the function. So we're not exactly there. By the way, solving this is essentially asking this question. If I add 11 to both sides, I'm really actually doing this math, I guess it's technically plus or minus. When I start with an initial value of x is equal to 3, I'm actually solving or approximating the positive square root of 11 through this procedure. So you can set up these initial equations or initial functions so that they can approximate square roots or cube roots or different types of roots for you as well. Anyway, let's go back to Newton's method of doing those iterations and see if we can come up with a solution for this. First of all, we know what the function is. F of x is equal to x squared minus 11, and Newton's method is going to require us to also know the derivative, which is a nice easy one in this case, 2x. The formula is xn plus 1 is equal to xn minus f of xn over f prime of xn, and so I can start by finding x1. So x1 is x0 minus f of x0 over f prime evaluated at x0. And so x0, that's 3 from our initial. And then f of 3 divided by f prime of 3. So I look at f of 3, that's 9, take away 2 is negative 2 on the numerator, and I use the derivative to do the bottom part over 6, and I grab a calculator to calculate this, and I get 3.3 repeating. While you're doing this procedure, it'll be very useful to learn to use the storage buttons on your calculator. So I would store this as the letter A on your calculator. If you're following through with this, I would actually grab your calculator right now and do this. Make sure you know how to store things in, follow through, see that you get the same numbers. Let's go on to x2. So x2 is the same as x1 minus f of x1 over f prime of x1. And don't forget, we've got x1 stored as the letter A. So x1 is A minus f of A over f prime of A. If you have this formula and this formula as your function and derivative, it's actually easier to just use a squared minus 11 over 2a. Make sure you use brackets so you get that bottom part. And on your calculator, you are doing 3.3 repeating minus 3.3 repeating all squared minus 11 over 2 times 3.3 repeating. And you are getting a new value, which is x2. And that approximately is 3.316 repeating. Now we can store that as A. And the reason that we want to store it again as A is we've already got this on our calculator, so you can use the recall feature on your calculator to bring that formula back and hit enter again with the new A value entered, and it should automatically generate x3 for you because it will do this, which is x3 is equal to x2, which is stored as A minus f of x2 over, and you used a squared minus 11 over 2a, hopefully with brackets, and you go and generate a number that looks approximately like, I don't know, 7, I think it's a 9 that's next. Now, as I said earlier, we are basically generating the square root of 11, and if you grab your calculator, you can see that the square root of 11 is pretty darn close to this. In fact, there's almost, not too many decimal places difference, and we only did 3 iterations. So Newton's method is a whole lot faster and a whole lot more efficient than the bisection method, which we learned to find roots back when we were studying the IVT. Let's take a look at one more example of this. Okay, we'll start with f of x being this cubic function, and cubic functions have up to 3 real roots. This one has 3. We can confirm that by doing part A, which is to use a graphing calculator to graph f of x. Go ahead, grab your graphing calculator, pause the video, and graph f of x. You should get a function that looks approximately like this. And you can see that it has 3 real roots. The next thing that we're going to do with this is we are going to determine what initial values would move towards or find each of those roots. So from understanding what we were doing, if we took an initial guess here and you found some point up here and then you used the tangent line and then you did it again, I think quite quickly points over here are going to tend towards this third root, the highest root. If you took a point here and you did a tangent line, you end up here and over here, and it does the same thing. Same thing here. As soon as you move over to this side, then your tangent line's going to get you here, and then here. It looks like I'm tending to move in this direction. Over here, the tangent line is going to go towards that point here, and you may notice that if you choose points here and here, well, that point will generate one over here, and that point will get really close to here. So you can kind of see there's 3 different zones. The zones are actually quite well delineated or differentiated by these maximums and minimum points. You see the red zone between here and here tends towards the 0 here, and in this orange zone it tends towards this 0 here, and in the green zone tends towards this 0 here. So what initial values find each root? Well, if we call this root 1 and root 2 and root 3, then values smaller than here go towards root 1. So for root 1, we've got values from negative infinity all the way up to whatever value that is. It looks to me like it's 0 on the graph. And then for root 2, somewhere between 0 and whatever value this is. Well, I can find out what value that is. I just need to find the where the slope is equal to 0. So if I find my first derivative, which is 3x squared minus 6x, I just need to set that derivative equal to 0, and I can know what that value is right there. So factoring out a 3x leaves me with x minus 2. That confirms that this one is actually 0, and then x is equal to 2 is this other point. So from 0 to 2 it looks like those values are in that red zone, and then the green zone are 3 would be found by taking values bigger than 2, which goes up to positive infinity. Oh, and you may have noticed my little mistake here. I'll just simply correct that. That's from negative infinity to 0. Third question is, what happens if we had an initial guess of 2? Well, some weird stuff, because right at this point here, I have a tangent line, and then I can't generate an x-intercept because it never touches the x-axis. So Newton's method is pretty fantastic if your initial guess is pretty fantastic. If your initial guess happens to be at one of these horizontal tangents, then Newton's method fails. And I'll leave it to you to look back on the equation and see if you can understand why, when the derivative is equal to 0, it doesn't work out. Anyway, enjoy the homework, pre-calc questions, and we'll see you in class.